Okay.
All those.
Nothing else. Okay. Implementation of semaphores. Okay, we're going to start from the beginning just for those other 24 people very quickly. But so because we are semaphores, they're used a lot. And so because they're used a lot, most computer architecture has this like operation called test and set. We're going to start out basically just looking at how it works, and then as we go on through this section, we'll look at how it works in regards to semaphores. So what happens is you're going to have, like for one process, you're going to have this variable x, and then you're going to, when you call test and set, you're going to have a register. You're going to put whatever value x has into the register and then set x to 0. That's all that happens in test and set operation. So this basically is just showing how test and set works. So, and this is implementing a lock using test and set instructions. A lock is a barrier through which only process can pass at a time. And so test and set is going to allow an easy implementation of a lock, right? Because, you know, and so we could use a lock for a critical, to like protect a critical section. That's an example. You have some code, you only want one process to implement it. You can use test and set to implement a lock. So let's look at this here. Okay, so we have two processes, P1 and P2. They share a lock implemented using a test and set instruction on a shared variable x. So that's how they share the lock, is they share this variable x. R1 is a register for P1 and R2 is a register for process 2. Initially, x is equal to 0, implying that neither process may pass the lock. And so the initial values of R1 and R2 are irrelevant. Okay, so they're just kind of there. Process P1 is going to execute this test and set, which copies x into R1, because that's what the test and set does. You copy whatever is in x to R1, so it's currently 0. And then since R1 remains 0, because this is while R1 is equal to 0, just do this. So it just kind of sits here, okay, at this line here. P1 continues executing this while loop repeatedly. Okay. Let's go on. So it's kind of stuck there. Similarly, the test and set of P2 copies x, which is 0, into R2 and sets x equal to 0. Since R2 is 0, P2 also keeps executing this while loop repeatedly. Okay. Both P1 and P2 are waiting inside their while loops for the lock to open, so they're both kind of stuck. Later, a third process, P3, will open the lock by writing a 1 into x.
So,
yes.
Like last time, this while loop is not actually doing anything. It's just
it's just blocking.
Blocking. Okay.
Yeah. And we're going to see in a minute, it's actually a waste of CPU time, because when it's blocking, basically on this loop, the CPU's got to check, you know, and make sure what that variable is, right? What's in that register. So we're going to look at some ways around it.
So what's the third process for?
It's just like a third process is doing something. It's just an example. So it's just like a third process comes along. So they're just all kind of doing something. This is just showing how you can set a lock and how you can unlock the lock, like an example of doing that. They could be doing anything. Okay, it opens the lock by writing a 1 into x. So whichever processes reaches the test and set first copies the 1 into the register and sets x back to 0, because that's what test and set does. So P1 executed test and set first, and so now it can go to the next instruction. Since R1 equals 1, process P1 passes the lock, continues, while process P2 remains. So we could rewrite this code a little bit and have like x equals 1. Let's say we did it this way. Let's go back to 1. I could have here an x equals to 1. And then this one would be able to, x equals to 1, when it sets it, one of these then would be able to like continue. That would like basically open the lock. So when you set x equal to 1, x equal anything but 0, it opens the lock. When you set x equal to 0, it closes the lock. Also, I mean, when you call test and set, it closes the lock because it sets x to 0. Sorry, that was a little confusing. Test and set only is going to basically set x to 0 and then kind of like copy something into the register. Then somewhere else, like if you wanted to change x to something besides 0, you don't use test and set for that. That's just like an operation you can do. So you can just use this for a lock. Like they show an example with 3 processes. Again, like if you had 2 processes up here, you could open the lock up here, and then one of them, whichever one gets to test and set first, would go in. So you can use test and set in different ways to like protect code. It's just a different example. Is this kind of making sense? We've looked at different ways of protecting code. You know, we looked at that thing where we had like the wheel weight and what was the other variable? There was like 2 variables.
C1 and C2.
Yeah, C1 and C2. We've looked at semaphores. With those, we've looked at critical sections and what? The bounded buffer problem. Those are 2 things that are like the consumer-producer problem. So, yeah. Today, we're basically just looking at using this test and set to do the same kind of thing. This is like the simplest way to do it. Okay, let's do this really quick. If r equals 1 and x equals 0, then after executing test and set, the values become what? Of r and x.
X will be 0.
Yeah, x will definitely be 0, because after we call test and set, x is always set to 0.
R will be still 1.
R will be 0. Because what we do is we write x into r, and then we set x to 0. So it will be this one. Okay, if r equals 0 and x equals 1, then after executing this text, and what is it?
We know x will
Test
be
and set.
0, right?
Yes. So x will always be 0. The values become what?
R will be 1.
Yes, because we're copying x into r and then set it to 0. Okay, if r equals 2 and x equals 1, then after executing test and set, the values become what?
1 and 0.
Yeah. So we're overriding whatever's in the register with what's in x. That's what we do. And then x becomes 0. Okay. These are slightly confusing, as these questions tend to be, but we'll go through them and we'll talk about them. R must be initially 0 for the lock to work correctly.
No.
I answered this. I can't remember what it is. I mean, what do they mean by work correctly? Okay, the initial value of R is irrelevant because test and set is executed at least once and copies x to R. When x equals 0, no process can pass the lock. True or false?
True.
No process.
No, true.
Okay.
Maybe P1 can't, but
It's according to how you set it up. Again, this is according to how you set up test and set. In this code, true. In the code they gave us, no. The way they set it up, you can't pass the lock when it's 0. You could set it up differently. Once a process passes the lock, x immediately becomes what?
0.
Yes, x always go back to 0. So, okay. The lock using the test and set instruction would work equally well if all zeros were replaced by 1s and vice versa, including test setting x to 1 instead of 0. So if we just reversed everything.
True, right?
It should be, because it's like, yeah, because it's just like, it's binary basically, so, you know, you could just reverse it. Okay. Okay. This is another type of semaphore. So we've talked about test and set. We will go back to that later. So that's just kind of an introduction. Actually, we're going to talk about it now. So there is a type of semaphore. So we talked about semaphores yesterday that are called binary semaphores. It's like a subset of a general semaphore. And it can only take the value 0 or 1. So this binary semaphore, instead of it having a P and a V function, they're going to call it PB for like whatever P stands for, binary, and then VB. So that's the binary. Or this
increment and decrement.
Yeah, that would be so much easier. I'm not sure why we, or said, and I don't know. They're the simplified operations that manipulate binary semaphores. These functions are on the binary semaphore can be implemented using test and set. That's why we talked about it. Okay, so here we go. We are going to have this variable SB. It is like just a variable that's shared between the processes that are using the semaphore. If we call this function, we set that variable to 1. If we call this function, we do test and set, which is going to set our shared variable to 0, and then whatever its value is copied into a register, whichever register the process is using, while r equal to 0. Okay, so this looks a lot like the other one. It's just binary. Okay. This is what we were talking about earlier. Busy waiting is the act of repeatedly executing a loop while waiting for a condition to change. Busy waiting consumes CPU resources and should be avoided. And so we are the next section that we'll talk about how to avoid busy waiting.
Busy waiting is the while r.
Yeah, it's like that while. Yeah. Because basically the CPU has to go check there every so often because it needs to know when it, is invalidated so it can continue. The implementation of the PB function using test and set is very simple, but it does do busy waiting. Okay, so let's look at this. So this is synchronization problem using binary semaphores and how it works. Okay, so yesterday we talked about semaphores that use a mutex, so this is the same thing, okay, as far as they're both going to use this mutex variable. And this is solving the critical section problem. So we have a single semaphore used. In this problem, it never exceeds the value 1, therefore a binary semaphore mutex with the two functions it uses is sufficient. Okay, only one process at a time can pass the mutex operation. Okay, so that's the critical section problem. Basically all you do is you have this mutex, you set it to 1, and then you put this function ahead of your critical section and this one at the end, and it will protect the critical section. Basically, what do I mean when I say protect the critical section? It just lets like one process use it at a time. Also, what is it going to do? What are the other things we talked about that are important besides mutual exclusion? There's 3 things. Yeah, lockout, deadlock, and of course now I can't remember. Oh my gosh. Starvation. Yes, starvation. Those things. This will protect from all of those things. Okay. So this is how it protects the critical section. Okay. It also works in the bounded buffer problem. What's the bounded buffer problem?
The looping.
Yeah, it's like the looping circular thing, and we have producers and consumers. And what do we have to ensure for producer?
Doesn't reach the
stuff
that hasn't been consumed yet.
Yes, it doesn't overwrite something consumed, and there is a place to put something. And then what do we have to protect the consumer from? There's always 2 things too, and I get
stuff that hasn't been produced yet.
Yes, so making sure there's something basically to consume. Okay, so that's how it's being used there. So initially we're going to have we're going to have 2 variables. We're going to have an empty variable, and we're going to set it to 1, and then because initially basically it's like true and false. So the buffer is going to be empty at the beginning, it's not full. And then we can use this binary semaphore to protect the data, like we have the produced data, and then we have this PB of empty. And then, yeah, let's kind of go back here. Initially empties 1 and full 0, so only the producer can continue while the consumer is blocked. And then when data is placed into the buffer, full becomes 1, and the consumer can continue while the consumer can continue while while the producer is blocked. That is wrong.
So
Yeah, so I need to.
if you have like n cells or whatever,
Yeah.
this makes it so that like the producer fills up everything it can, and
Yes.
the consumer consumes everything it can,
Yes. Yes.
instead of being like more
Like back and
simultaneous.
forth. Yeah. Yeah. That's true. That's how this one works. And there's like, I think in the last section, there's like pros and cons to those different approaches. So that's how this works. Okay, they do not talk about this at all. So we're just going, so you won't know the answer unless you've done this already. But we will just talk about it. So a process P executes a critical section in 5 units of time when running alone on a CPU. When 9 other processes, all time sharing the same PU, are trying to enter the critical section, and basically they're blocked, P will need how many time units to execute? So there's like 1 that's actually executing and 9 that are blocked, waiting.
So
And they don't talk about like that calculation.
each 9 processor 5 minutes.
Yes.
So
Yeah.
Then it's 45. So about 50.
It's 50. Yeah. So what happens is the 10 processes, they're all running. And so while it's running for 5 units, the others are waiting for 5 units. The other 9, right? They're blocked. And so it's a total of 50 time units.
That's assuming that P runs last. I mean, because if P was
Yeah.
not blocked initially, then it would still be 5.
Okay, so the idea is like P actually enters the critical section. It runs for 5 units. And then during those 5 units, the others are waiting, but they're using they're not blocked. I shouldn't say blocked. That's misleading. They're busy waiting. So that they still have to be run by the
So it's
CPU.
still switching to them.
Yes.
Okay, so that's why you need 50.
Yeah, that's why. Yeah, the blocked, no, we're going to talk about that. Blocked actually will help, being blocked. But yeah, they're actually just kind of on the CPU. So it takes 50. Yep. Okay. Does that make sense? Okay. Placing a data item into the buffer takes 10 milliseconds when executed in isolation. Similarly, the removal of a data item takes 10 milliseconds. When the producer and the consumer run concurrently on one CPU, and the producer begins filling the buffer at time t, the consumer will finish emptying the buffer at what time? Okay, so the idea is the producer has to busy wait, the consumer's busy waiting while the producer's producing. It's like spinning. And then vice versa. So it's like when the producer's producing something, that takes 10 units, and then the consumer's waiting. And then while the consumer's getting the thing, the producer's, waiting. So that what would that be?
Is
That's
this
like 2.
40?
Yes,
Plus
it's 40.
Why is it 40?
Yeah. Okay, so while the producer's placing data into the buffer, the consumer's busy waiting.
Yeah.
And so that's 20. And then, so opposite, when the consumer is consuming, the producer's waiting. And so that's also another 20. So that's why it's 40.
Because you're starting accidentally waiting for this certain amount of waiting.
So basically, what those are just showing you is that busy waiting wastes time. And we're going to look at a different way to get away from busy waiting. We're going to look at a different method. So it's an option, but any questions?
I don't know.
You're starting accidentally.
Yeah. Oh, these last 2.
Yeah.
Oh, you're printing the thread though.
Yeah. I mean, the main point from that is just that
Yeah.
if you set up something using like a binary semaphore or like a test and set that involves CPU, it still involves a CPU. And so just to be aware of that. Okay, what time is it? Oh, okay. Okay.
Stories all in a global variable. So bring the thread to the global variable.
Okay. Excuse me. Okay, so we've talked about test and set, and then we've talked about how you can use that in a binary semaphore. And yesterday we talked about general semaphores. Okay. And so we're going to talk about how you can use the basically you can use PB. Let's go up to here. And VB, which use test and set for the general. So it's just basically building off the last semaphore we learned about, or we talked about how you can build it using these two functions. And basically in these, SB is going to be 1 or 0. Okay. Because remember, SB is like the X that we talked about earlier. Right? When we talked about test and set, you have an X and a register.
Mm-hmm.
So X is going to be 1 or 0 in this case with these binary semaphores. Okay. So we're just kind of building off of each idea. Okay. Okay, a general semaphore can be implemented using a regular integer variable manipulated by these functions. To guarantee that only one operation at a time can access and manipulate S, which is just the shared variable, a binary semaphore is used. This shared variable is going to serve two purposes. When S is greater or equal to 0, S represents the value of the semaphore. Whenever it falls below 0, so it's like going to be 0 or 1, but it's going to actually fall below 0 sometimes using this implementation, and that's going to represent the number of processes blocked. So it's going to be 0 or 1, you know, basically. It'll be, to let things through, it'll be 1. When it becomes 0, we're starting to block, and then the further it falls, it's going to be however many more processes are blocked. So let's just look at an example. Okay. Okay. Here we go. So this is just using PB and VB to implement a semaphore, a general semaphore. Okay. So the implementation of P and V uses a shared integer S to represent the semaphore. A waiting list is associated with S where blocked processes wait. Okay. PS is going to decrement S in a critical section implemented using the binary semaphore MS. So this is a shared variable. If S is less than 0, the process blocks itself. Okay. VS increments S in a critical section implemented using the same semaphore. If S is less than or equal to 0, one or more processes are blocked. Okay. So let's just look at how it works. Okay, if S equals 1 initially, a process P1 decrements S. Since S is not less than 0, the process completes and leaves. If P1 repeats the same operation, S becomes -1 and the process blocks. The value S equals -1 indicates that one process is blocked. When another process, P2, tries to pass, it's again decremented and it becomes -2. So a subsequent V operation increments S. Since S is less than or equal to 0, V reactivates P1 from the waiting list. Okay, so it basically reactivates one process at a time and gets off the waiting list. So this is going to make processes basically have to block, and then this one's going to one by one let them leave this waiting list. Another VS operation reactivates P2 because there was like P1 and P2, and so semaphore is now 0. One more VS operation only increments S again, but no process is reactivated because there's nothing to activate. So what's happening here? Okay, PS is our general semaphore. If we remember back to yesterday, this function that lets us use semaphores. We're going to use PS. We're going to have PS use this binary semaphore, which uses test and set. So it's like, yeah, a bunch of things together. So PS and VS are basically doing the same thing they did before almost, except now our semaphore, because it's set up a little differently, the value of our semaphore, if it drops below 0, is going to tell us how many things are blocked, which we don't really, it's just something that happens. But PS is just going to block things, and VS is going to, basically PS is going to lock some processes, one or more. VS is going to let those processes like reactivate them. Why do we need these? We can use it for, again, critical section or bounded buffer. Okay, so this is just showing how, yes.
Is this the same as the original semaphore, but we're just using a binary one to do it?
Yes, except I don't remember if it dropped.
Right, the other one didn't drop, I don't think.
But it still does the same kind of, it still works the same way, basically. Yes, it's the same. You're just using binary.
But now we can go
Yeah.
below 0. Or,
That's what I can't, let's go look.
because I don't think the other one did that. I think it just went up.
Let's go look. Okay, general semaphore. Okay.
The goals, like you said.
Okay. We got a mutex. We use the mutex.
That's some difference.
Hmm.
Let's see if it's like actually switching between the two.
Okay, let me look at the semaphore.
Or, yeah, it's
Increment S by 1. If S is greater than 0, decrement it by 1. Otherwise, wait until...
Well, there's no 40. You're cheating 5 times.
There's no 4 loops anywhere besides in the file.
Yeah, so it won't look. You won't be able to tell.
It works.
Yeah. Probably.
Sorry, I'm just looking. Sorry, I'm just looking at it. No, it definitely doesn't go below 0. Okay. P.S. If S is greater than 0, decrement. Otherwise, wait until it's greater. Well, it actually does drop.
Never below 0 though.
That's true. So yeah, that's the difference.
So it's like a better semaphore because we get this behavior, but now we can tell how many things
Yes.
are waiting.
Yes. I don't know if it'd be better. I don't know if anything utilizes how many things are waiting. It seems like that could be useful, but I'm not sure.
Yeah.
Yes. So it's just a different implementation of what we talked about yesterday. Okay, there we go. And then they just show how to use it. Using, oh wait. Okay. So this is basically if we took the code for PS that we had and we just replace it with this. And then this is going to use the binary setup. Yeah. So that's what it's talking about. Okay. The variable S can become negative, which violates the definition of semaphores. Let's look at this. Can S become... Yeah, I know. I did this. Let's just say... Okay. S serves a dual purpose. When S is less than 0, the variable serves only as a counter. I don't know. That's a weird question. I don't think we've ever talked about the definition, that there's a certain definition, so that's just weird. But
Well, this is a semaphore S is a non-negative integer variable that can be accessed using only 2 special operations, P and V.
oh, in the other, where? Down here?
Back in the last section.
Oh, okay. So that should be a variable S can become negative, which violates our previous definition of semaphores because it's updated now. Because this is our new definition. So, S can be initialized to any integer value. No, setting S less than 0 would imply that one or more processes are blocked, which can't be true. So we want to set, because when we start, nothing's blocked. Okay. S equals -5 means that 5 processes executed when S was less or equal to 0 and became blocked. Yes. If you see X equal -5, that means 5 processes are blocked. S equals 0 implies that the waiting list on S is empty. Now this I have to go back to. Okay, let's make it. Yeah, then one or more processes are blocked. Oh. S is 0 is either the initial value or the result of the last successful operation, which decremented S to 0. Okay. The waiting list of processes blocked on a semaphore can become arbitrarily long. Yes, it can. Decrementing and testing S and PS is a critical section. They talk about this. It is. It has to be. Where do they talk about this? I think this was somewhere. VS increments S in a critical section implemented using the same semaphore. Okay. The operation VB of MS and PS could safely be moved after the operation block self on S. Ooh, okay. Let's go look at that. Okay. The operation VB and PS could safely be moved after. I don't think so. Let's see if I'm right. Yes. The process would block itself without releasing the shared variable, which would be bad. Okay. Let's look at these. Or what time is it? Oh, we got some time. Okay. The following implementation of PNV uses continue. I think we're gonna move on. Okay. Let's start this and then we're gonna take a quick break in a few minutes. Okay, monitors. So basically what a monitor is, it's like we're taking our P and V operations and our shared variable and kind of putting it into an object all together. And that's a monitor. So P and V operations on general semaphores are versatile primitives, but P and V operations are low level that are prone to difficult to diagnose programming errors. So a monitor is a high-level synchronization primitive implemented using the P and V operations. So we're going to have this like object that's going to have P and V kind of in, you know how like an object has like attributes and methods. Same thing. It's going to have PV and then a shared variable as its attribute. Following the principles of abstract data types, a monitor encapsulates data along with the functions through which the data may be accessed. A condition variable is this is something that's different that we haven't seen. A condition variable is a queue on which processes can wait for some condition to become true. So it's like we're going to have this queue that's going to hold all the block processes, basically, as part of this. We saw this in the last thing when we talked about binary semaphores. There's just some kind of place that you put things to wait, like a waiting list. This is the same thing, except it's just going to be called this condition variable, and it's just a queue. Okay, implementation of a monitor. It must guarantee that all the functions are mutually exclusive. So that just basically means our P and our V functions have to be mutually exclusive. Only one process at a time can be executed inside the monitor. provide condition variables so that a process can step outside the monitor while waiting for a condition and thus not prevent other processes from entering it. So we're going to have these two. We're going to have another variable called C that's going to have a wait and a signal. Okay. Let's look at this. So this looks a lot like just an object. We've got this variable X. We've got an F and a G. So monitor M has an internal variable X and two functions F and G. A process entering the monitor by calling the F function must wait for X to be positive before proceeding. A condition variable, X is positive, is defined for that. Process P is going to call this function and finds X equal to -1. So executing, because that's like when we start, X is -1. Executing X is positive wait blocks a process. When another process calls M of G, it's going to call that, and sets X equal to 5, the condition satisfied, and this signal basically will then call this one. They like interact with each other and reactivates the block process. So P1 can resume executing F and P2 can continue executing G. But the monitor definition says that only one process may execute inside the monitor. So what happens is when the signal is going to grant the block process the right to continue immediately while the signaling process becomes blocked. So whatever signals, when the signal happens, that one becomes blocked and the other one gets to run. That's the rules. Because only one process can run at a time in the entire monitor. When P1 exits the function, this process now is reactivated and can complete. So that's how those are going to work together. And we're going to see examples of how the monitor is used in like bounded buffer and how it's used, well, in some other examples. So let's see here. Should we answer these? Okay. A conditional variable can take any integer value. True or false?
Is it false because it's a Q?
Yeah, they're not traditional variables with values, but only names of queues.
Yeah, it's not like an integer type.
So it's like a nice trick question. A monitor contains internal variables and two functions. This is also, I'm not sure if this is a trick question or not.
They're
Yeah.
monitored it.
In this example, you can have as many functions as you want. In this example, we have two.
It's like they meant exactly two functions.
Any internal variable or data structure can be accessed only by calling one of the functions. Yes. This is something that's from basically object-oriented programming ideas, right? Where you can only access like the variable inside an object with the methods.
So their X should be private.
Yeah, so they should be. When multiple processes call a monitor function simultaneously, only one is allowed to execute the function while all others wait on the urgent queue. We haven't really. The urgent queue is used only for processes executing a signal. All processes waiting to execute a function are blocked at the entry. Oh, okay. CWait always blocks the calling process. Oh, man. CWait may be invoked inside a conditional statement based on some condition, but whenever the statement is invoked, the process blocks. CSignal always blocks the calling process, which is then placed on the urgent queue. I don't think it would always do it. Yeah. CSignal blocks the calling process only when there's another process waiting. Oh, that's fun. Okay. We are going to stop there. I will come back. We're going to talk about how we use this monitor to implement the bounded buffer problem. We're going to talk about monitors with priority weights. Different ways to implement the monitor. And if we get time, and that's it. So we'll finish monitors today. We should be okay with that. Okay, tomorrow my plan is, I think we just have one more section. Yeah, we are going to do the one more section and then just review, because this is a pretty involved chapter. So we'll kind of like hit the high points of the chapter. So if you could just look over, you know, tonight, look over this chapter, think about, because I can't actually, again, go through all 4 sections on one day, but think about the things that are like, you know, really, you're like, I have no idea what's going on, and then we'll talk those.
Chapter 3 and 4.
Yeah, but just the first 2 sections. So it's the last 2 that we didn't have on the test, and then the first 2. So yeah, so we can really like focus on these since you have the quiz, and then we'll also start talking through the other ones. So yeah, so focus on 4.1 and 4.2 also, since you have that quiz and you want to make sure you really understand tomorrow. Okay, so that's the plan. Okay, I'm going to go grab something to drink, and I will be back. Are we recording? Okay.
Someone's about to get unplugged here.
About me?
I'm not quite there yet. I'm at 95.
Alright, you're unplugged.
No.
I was first.
This is my plug.
Just unplug one of the other things. I don't need those. Really, those last 2 plugs are mine.
Eeny, miny, you.
That was a monitor, so that's good. This whole section is confusing. I need to reread it all.
I need to read it.
Probably.
And the last section.
I need to read it all. I feel like the Enchantress in this game does like a giant heal.
Ah, so it doesn't like
It doesn't just heal one person, it heals everybody, so it's OP. So it has all the goblin attacks, dude.
Faster.
Yeah.
Fast. Can you play game
Sure. You play it well like that?
Can you play PUBG?
I mean, you can. Can you?
Can you?
You just use fucking
That's not what it is.
I'm going to get you. Awesome.
Is that 600? Yeah, 600. Oh, 500 too.
PUBG requires you to.
They made
The 4 on theirs ain't that good though.
6.
Only 6? Or is it 10?
No, it's 10
It's alright. Yeah, but if they're warriors, it doesn't do shit to them.
They have warriors against us, but no one can stop. This is warriors.
I might take
Oh no, oh no.
Good job. I'm watching. Undead Passive sucks. Very bad.
Oh, survive. Survive.
Undead Passive, hot garbo. That is the combo almost. He has the big hit, as we call it.
See, they are going to be.
Dang.
But we can return it
Not the
from
big hit.
midnight or midnight.
It is. I might actually be good
Let's say
Yeah.
a day because there is
I have so much heat. Nobody dies.
yeah, but then it's
Goblin back. Druids. No one dies.
Kill him. Oh, I lost. Oh, no.
right.
I need tier 3 Enchantress.
Sometimes I wonder how to determine candies.
Yeah, I know.
Like this guy won, but he only got 1 candy. I got 3 candies.
All RNG.
So you get like for this. You for this.
Yeah.
Like for 25 plus.
Sonic?
Mm-hmm.
Sonic.
So which
I prefer Sonic.
Okay. So let's just finish up this section. We can go. Oh, I wanted to ask if tomorrow we could meet a little later because I have a doctor's appointment at 11 and they're very slow. So I don't know if I'll be done by 12.
Okay.
Like maybe 1.
One,
Is that too late? 1 to 3?
It doesn't affect me at all. So
Does it affect you? Are you okay?
It affects me.
Part of the class. I usually work at like 2:30.
Oh. Well, we should be. Yeah. We'll do the. I don't
That's
know.
fine though. If it works for most of the
We
class.
can do online
I mean-
class.
It's already basically 12. I'm 12:30. I don't know. Like I would like to start at 12:30, but they're very slow, so I'm just not sure. So I don't know.
can we start an hour early on June 3rd?
Can we start an hour early on June 3rd? What is that day? Maybe?
WWDC,
What?
Worldwide Developer Conference.
Oh.
Yeah, I don't think
They start live streaming it.
Oh, they do? Yeah, I'm okay with that, maybe. If everybody else wants to.
No.
It's fine. Okay, so you know what? I should hopefully be out by 12:30. Let's do 12:30. And then it just watch the email at 12 if it's looking dicey. Like if I haven't gotten they're just the slowest people in the world. Then I will email you and we'll meet at 1. But if it's looking good, then we'll just start at 12:30. Does that make sense?
Yeah.
So I'll just kind of
Just say
update you.
one works for me, and I can stay till 2:30.
Okay. Yeah, we'll do. I think I'll be done. But just on the off chance, just watch your email. And if it looks like it's not going to happen, we'll just meet at 1. So, okay. Thank you. Okay. And so we have this bounded buffer problem where we have this circular buffer and we've got a producer and a consumer that are kind of they're having to work in tandem with each other. And so we can use a monitor to implement that. We've looked at all these different, ways of implementing the bounded buffer problem. So this is just another one. So monitor primitive is a simple solution. Because the monitor guarantees mutual exclusion, the functions to deposit and remove data become critical sections. Because the monitors, that's just how it works, it's mutually exclusive. So the solution works for multiple producers and multiple producers because of that also. There's a condition called not full. It is used by the consumer to wait when all buffers are full. And there's a not empty that's used by the consumer to wait. There is a counter full slots. It's set to 0. It's used to keep track of how many slots are full. Counters incremented by the producer and decremented by the consumer. So let's just look at this. So we've got this monitor, 3 variables, 2 functions, 1 to deposit, 1 to remove. Again, this whole thing's mutually exclusive, and the only thing that has access to the variables are these 2 functions. Okay. We have a buffer. It's an array accessible via the functions. There's our buffer. Deposit and remove. All slots are empty, so full slots is 0. If a consumer process calls remove, then C1 becomes blocked on the non-empty condition, right? Which makes sense because if there's nothing to remove, we need to wait. Okay. So we have these 2 kind of blocked things. Okay. A producer process P1 calls deposit. Since there are free slots available, so that's where it would block if there wasn't a free slot, it would wait over here. Then it's going to place data into the buffer, increment full slots by 1, and signal a process blocked on not empty. Okay. C1 re-enters the remove function, so now it's unblocked. Actually it's just re-entering. Removes the data from the buffer, decrements full slots, and signals the not full queue. There's no block process, so it doesn't do anything. If producers run ahead of consumers by n steps, then all buffer slots can become full, so all subsequent producers will be blocked on not full until at least 1 slot becomes empty. And then, as long as full slots is greater than 0 and less than n, all producers and consumers will proceed without blocking. So this is, and that makes sense because you only want to block basically if there's nowhere to put something or nothing to consume. Otherwise, you just keep adding. And again, mutual exclusion, because the monitor is mutually exclusive, right? So one's going to produce, you're allowing one to come in at a time, and so there's no overriding or anything weird like that happening. Okay, or no like inconsistency of like these variables and stuff. Okay, is happening. So the producer may proceed when full slots equals greater than 0, less than n, or equal to n.
Less than, or wait.
It's a little, let's see. If it's n, we are going to wait.
Yeah, less than n.
If it's less than n, we keep going. The consumer may proceed when full slots is greater than 0, less than n, or equal to 0. So,
Greater than 0?
Yeah.
Can't be equal to 0.
Because it waits when it's equal to 0. And if we think about why, that makes sense, right? It's waiting because there's nothing to consume. And then the code segments place data into the buffer and remove data from the buffer must be implemented as critical sections to prevent multiple processes to manipulate the buffer array simultaneously. Always, only when multiple producers and consumers are sharing the monitor, or never. Gonna wait. Coming in. They're mutually exclusive anyway. Okay. But they, oh my God. Okay. They are critical sections because it is. So that's kind of a tricky question. It's just trying to say, like, do you need extra code? Oh, okay. Do you need extra code in here to make a critical section? No, you don't, because a monitor is just a big critical section. So it's kind of a trick question. Okay. Okay. Monitors with priority waits. So normally a queue associated with a variable, so like here we have these queues that are used, like that things go on when we're waiting, they just go into these queues. Is processed in first out order. Some and they haven't really talked about that, it's just been kind of happening. Like the first thing there is the first thing out. Some applications require additional control over that process reactivation. So a priority wait has this form where C is a variable and P is an integer specifying the priority according to which process is blocked on C or reactivated. So basically in this queue that we're kind of putting stuff in, maybe we need to have some sort of like algorithm running, based on priority. And so they're going to have a priority. So let's look at that. That's kind of what's going on. Okay. So we have this thing called a monitor. It's a monitor. It's called alarm clock, and it provides a facility for processes to be blocked for n number of time ticks by calling the function wake me. So this is just some kind of monitor that's doing an alarm clock. You could do a monitor to do anything, and it's going to use this priority, like it's going to use a priority waiting queue. They're going to have a shared variable. It's called now, and it's set to 0, and it's going to keep the time. Okay, we're going to have a condition variable called wake up, and it's provided for processes to wait till they wake up. If P1 calls wake me 3 at time 10, then P1's alarm setting is going to be 13. Since now is less than 13, P1 is blocked. Okay, so it's basically saying wake me in 3 time units, and so it's going to set this thing to 13, and it just waits.
3 time units from now.
Yes. So now let's say if now was 10, like the thing's running, now is 10, and it says I want to be blocked for 3. I want to wake up in 3 cycles, then the time that it is the 13th cycle, or whatever we want to call it. So if P2 and P3 call wake me 1 at time now equals 10, then their alarm setting is going to be 11. And so they're also blocked because like it's an alarm clock, so it's like in the future. So they're all waiting. So a hardware there's another thing called tick. A hardware interrupt periodically calls the function tick, which increments the current time by 1. Okay, so they just have this way of incrementing now. Okay. The function issues a signal to the first process, if any, blocked on the queue. The problem is that P1 would wake up before P2 and P3, even though their alarm settings are lower. That's not good. So there's something called priority weights. So using priority weights with this alarm as a priority, the alarm setting keeps the processes sorted in an increasing order. So this is just something that's there. So now they're there. The next tick increments now to 11. And the signal is going to reactivate this one. Since now equals alarm setting, P1 is going to exit the loop. Before leaving the monitor, P2 issues a wake-up signal to assure that if the next block process has the same alarm setting as P2, it's reactivated. So that's why that's there. This is just for all the ones that have the same time as the current. If we had some kind of condition that you can't have 2 alarms set for the same time, you wouldn't need that instruction. Oh my gosh. Okay. Okay. Process 1 calls wake me 5 when time is 0. Process 2 calls wake me 5 when the time is 0. Process 3 calls wake me 3 when the time is 0. Process 4 calls wake me 1 at time 3, which is going to leave the monitor first. This is basically just addition. So 5, 5, 3, and 4. So it should be process 3.
Yeah.
Okay. Ooh, okay. A function tick will be invoked how many times before the first process leaves? So if it gets there at 0 and it leaves at time 3, then it's going to be ticking how many times? 3. That makes sense? Okay. Which process leaves the monitor next?
P4.
Yeah. Which leaves the monitor last? Well, we don't, I guess if...
Is it like a... It said it was first in... It's not first in, first out.
Well, it's going... Okay, if P1 calls before P2, it should be P2. That's really kind of a weird question, though.
Because it puts the new ones like on top of the stack.
Yeah. It's a priority queue, but then the ones that are basically the same are like first in, first out. So if P1 got there first, P2 would be the last to leave.
If, let's say, if you had 3 processes that were all supposed to end at 5.
Yeah.
Call them P1, P2, P3.
Yes.
Would P3 be the one that would leave?
Yes.
Or was,
Yes, it
was
would.
it last? Or?
It would leave last. Because P1 would be signaled, and then it's going to go through and it's going to signal the next one, because there's that piece of code here. This wake up signal will signal all the other ones with the same time. So it'd be P1, P2, and then P3. And then the tick happens, and then it goes through again. So this signal here calls this wait, and then the wait, if there's something to wake up, I mean, it's going to wake up, you know, basically everything at that time signal. And then, I mean, at that time, excuse me, and then this signal will signal all of the rest at that same time.
But wouldn't the tick, it would signal, in my example, it'd signal P3.
The tick won't run again. So, like, let's say...
The first, like, when you get to tick 5.
Yes.
And then it signals P3.
Yes.
Because that was the last one added. And then it goes, okay, we're waking up. So then it calls wake signal to P2. That one wakes up, and then it calls wake signal to P1.
So, it's gonna call the wait. Okay, if the P1 was the first one that got there, it's gonna call P1. It's gonna wake it up. P1's gonna wake up, and then that's gonna call P2 and P3. And P2, it'll call P2, and then P2 will wake up P3.
So it doesn't start with P3; it would start with P1.
Yes.
Okay.
Yes. If the wake up signal was omitted from the wake me function, then P2 would leave the monitor at what time? It would leave at the next one, so it would leave at time. What are we time? Yeah. Yeah. And that would be too late, so that would not be good.
And you
Okay.
get people calling and saying the alarm clock app doesn't work. Get woken up half hour late.
Exactly. Let's see. The process at the head of the wake up queue may have to re-enter the wake me function and become blocked again multiple times before being able to leave the monitor. True or false? Okay.
Yeah.
Let me make sure. So the process at the head of the wake up queue may have to re-enter the wake me function and become yes. Because of it might not be time yet. There is no need for the urgent queue in the alarm clock monitor. I mean, we're not using it because we have a priority. Okay. Okay. Implementing a monitor. So, what we haven't seen is like the nitty-gritty details of how this monitor is implemented. And so, do we? Yeah, okay. We have to have all these things. We have to have a semaphore mutex, which is initialized to 1 to enforce mutual exclusion. We need a semaphore C, which is initialized to 0, and it's used for each conditional variable to allow a process to block itself. We need a semaphore urgent, which is initialized to 0, which is used to block a process executing a signal. Associated with each semaphore is a counter, which keeps track of the number of the processes blocked, and associated with each semaphore urgent is another counter, which keeps track of the number of processes blocked. So this is what they look like. We have for whatever function, like if there's a deposit function in this example, or remove, like for the bounded buffer, we're going to have this mutex and then this code here. And then for the wait condition, we're going to have all of this. And then for the signal, for the conditional variable, we're going to keep all of this fun code here. That's how it's actually implemented. So it's just replacing. Okay. So we have this compiler. It's implementing the function deposit on the bounded buffer. And we're in this monitor. We have this monitor. So we are saying, you know, it's mutually exclusive, and we're going to have all these conditional variables as part of the monitor. The compiler inserts the code to enforce mutual exclusion. That's this mutex that it's going to use. And that is going to guarantee one process can be executing. Before executing the function, the process has to release the mutex. If another process is blocked on the urgent queue, then the block process is reactivated. So basically, if there's something on the urgent queue, we're going to reactivate that thing on the urgent queue. Otherwise, there's nothing and we just leave. Either way, you leave, but basically you're saying, should you reactivate something that's on the urgent queue? Okay, so that's mutual exclusion. Then we have this not full wait and not empty signal that we talked about, which is going to basically make sure that we wait if there is nowhere to deposit something, and when we actually deposit something, we signal to the consumer. Both of these have to be implemented low level using this code. Okay. before blocking itself on P not full, the process releases the mutex. Or if the urgent queue is not empty, the current process reactivates the first process from the queue. So two things happening. We are going to release the mutex. Okay, so if there's something urgent, we let it go. Otherwise, we release the mutex. And then we are reactivating. Yeah. Okay. Urgent queue. Okay. So kind of basically the same thing. Either we let something that's on the urgent queue be released, or we just release the mutex. Okay. We have this code here. This not changing because this is the only thing that has to be compiled into lower level. To record that one more process is blocked on the not full queue, there's going to be this not full count prior to blocking. So that is added. That's a different variable that we don't have. And then for the signal, that it's basically when it finishes so that the remove can continue or can be used, we're going to have if not empty count is greater than 0, we reactivate the waiting process and block on the urgent queue. And then urgent count is incremented before the signaling process blocks itself and is again decremented when the process resumes. Okay. So that is very fun. That is not fun at all. Okay, we need something, some kind of activity to do for this or something because this is very complicated. So I will come up with that and we'll just have to work through it. This is huge, like really long. Okay, to see how a bunch of processes block on this. Okay, this is basically just matching. So we just look and see like not full dot wait, and then we can just go look and see what the code looks like. So we have some kind of counter, and then we have this, and then we decrement. So I'm going to say this one. So I'm just doing matching here. Okay. Yes, because like up here's like the generic code. And so I'm just matching the generic code with what we're doing there. Okay. So I don't know if this is really helping us, but if we have this counter greater than 0, that's going to be this one, the signal. Okay. Okay, this one we are going to be incrementing by 1. Oh, okay, so it's going to be opposite of wait, so it should be the, oh wait, it's going to be this one. Yeah, this is the signal. We're going to stop there. Okay. I need to make some kind of activity, so I'm going to stop here, and so we will just do that tomorrow. We're going to do a review and then go through the next section. So if you could look through this a little bit, so we can do a bunch of things on it over and over until it's there in your brain. We'll do that. Okay, any questions? Like, besides, how does this whole thing work? Because I'll do that. Okay. So yeah, just look at this. This whole section is really not bad. This was all pretty okay until we get to this fun thing here. So just kind of look at it.
It's weird. Some of it like makes sense, and then it gets to this spot and I'm lost, and then we go to the next thing and like, it makes sense again.
Yeah, that's why we need to review. So yeah, we'll kind of go over this again. Okay. So yeah, just kind of review today. Look at the next section. We're going to finish up so you're ready. We're going to meet tomorrow around 12:30. I will give you a reminder. I think that's about it.
What's
Yes.
the quiz covering?
It is covering 3, 4, 3, 5, 4, 1, and 4, 2.
But isn't it 3-6?
There's no 3, 6. Yeah. So, yeah. So, also, if you have questions about those, come with that. Yeah. Okay. Cool.
And that bonus was due tomorrow.
That's
Yes.
tomorrow.
That is due tomorrow.